Hey guys, Dr. Betts here coming with another fantastic chemistry video, and today I'm going to talk about chirality, a big topic in organic chemistry, big topic in biochemistry, big topic in biology, big topic in cell biology. It's a big topic. It matters. Now, chirality means having handedness, so being handed. Just like humans, we have a left hand and we have a right hand. And I think everyone will agree, if they look at their left hand and they look at their right hand, they look extraordinarily similar. But if you look at your left hand and your right hand, you will also agree that they are essentially mirror images of each other, discounting hangnails, fingernails, and all that other scars or whatever. They are mirror images to one another. So they may appear to be the same, they're mirror images, but when you try to superimpose one onto the other, that means lay one, let me get on the camera here, lay one flat on top of the other, you'll notice no matter how hard you try, you can never get your thumbs to line up when your palms are lined up. You can never get your palms to line up when your thumbs are lined up. You can never get your pinkies to line up when your thumbs are lined up. It doesn't work. Your hands are mirror images, no doubt, but they are non-superimposable, which means you have what's called handedness. You have a left and a right hand. An object is chiral if its mirror image is different from the original object. So just like your hands and your feet, they're chiral. You have handedness. Now, achiral things, let's take, for example, this marker. If I were to get another one just like it and put it side by side, you all will agree these two markers are mirror images of each other, but I could easily superimpose one onto the other and have exactly the same thing. So these markers are an example of achiral things. The mirror image of one will overlap with the mirror image of the other. So the mirror images will overlap each other. So these are not chiral. These are achiral or not chiral. All right? So there's chiral things and there's achiral things. Chiral things, mirror image, will not overlap at all, will not superimpose at all. Achiral things, the mirror images will certainly overlap, just like those pens I just showed you. Stereoisomers. Now, in chemistry, molecules can have handedness as well. You can have a left-handed version of a molecule and a right-handed version of a molecule. And they're similar but different. Just like in your hands, one will not overlap with the other or superimpose. And in chemistry, we don't call that handedness. We call that having a pair of enantiomers. Enantiomers are non-superimposable mirror images of each other. And here's an example. Notice how this particular molecule, if you pick it up in your mind's eye, move it over here, and try to drop it down onto this one, even if you turn it, twist it, rotate it, do whatever you want to do, it will never superimpose on top of the other one. It will always have two atoms out of place, no matter what you do. And that's called being a pair of enantiomers or having handedness or being chiral. Now in chemistry, especially in organic chemistry, we have these things called chiral carbons. That's how we can identify quickly if a molecule is chiral or not without having to draw mirror images and trying to superimpose. A chiral carbon is also known as an asymmetric carbon. We call it that as well. And they're identified by looking at a carbon and identifying 4 different chemical groups that are attached to a carbon. For example, if we have a molecule like this, say there's a bromine here, chlorine there, and say we have an OH coming out towards us and a hydrogen going back away from us. This molecule is chiral. How do I know? 4 different chemical groups are attached to it. That's how I know. Let's draw the mirror image real quick. There we go. So this and that are mirror images. Now, if you pick this up in your mind's eye and drag it over here and try to superimpose it onto this molecule, you'll notice very quickly that they do not overlap. You can turn it, twist it. The only thing you cannot do is break bonds. But you can turn it, twist it. You can manipulate it any way you want, just can't break any bonds. And you'll see that this will never overlap with that. It'll never happen. Stereocenters. Now, in organic chemistry, we have these things called stereocenters. They're also referred to as chirality centers, stereogenic centers, or stereogenic atoms. Now, you don't have to be an atom. You could also be a group. But for the most part, we're going to be dealing with atoms, okay? So let's see some examples of that. Of course, we've already seen one, the chiral center. And I'm just going to draw a carbon atom with 4 different groups attached to it. How about a methyl group? And how about an OH over here? Something like that. So this carbon is a center of chirality. We call it a chiral carbon. It could also be called a stereogenic center. It's all the same. Double bonds can also display stereogenic centers. This is a stereogenic center, and so is that, because you can invert them. Now, for example, we could take this molecule here and draw its trans version, or sorry, the cis version. And you have a stereoisomers. These are stereoisomers. They're not enantiomers. They're called diastereomers. We're going to get to those later on in this chapter. But these are chirality centers, places where you can just change one thing and have a different molecule. Achiral compounds also exist, and they're very common. They're probably more common than chiral compounds. One way to identify an achiral compound is to look at all the carbon atoms and look for an asymmetric center, or a chiral carbon, a carbon with 4 different groups attached to it. If you can't find one, the molecule is likely achiral, although there are exceptions to that. So here we have an example of an achiral molecule. Notice we have the same group here and here. We have the same atom or group, so therefore this cannot be chiral. Let's draw the mirror image of this real fast. There you go. So this is an example of an achiral molecule. If you were to pick this molecule up in your mind's eye, drag it over here, turn it, twist it, do whatever you got to do, you will see that this molecule and this molecule will nicely overlap onto each other because they are literally the same compound. They're telling me the same thing. Now, this is where students, I often encourage them, if you can't see it in your mind's eye, buy a model kit, a molecular model kit. They are extraordinarily helpful with organic chemistry, with organic chemistry in general, but specifically they're very helpful with chirality and stereocenters and assigning stereogenic centers. Very, very helpful with that. Once you get used to it, however, you probably won't need a model kit as much. Planes of symmetry. This is the other way to tell if a molecule is chiral or not. Look for planes of symmetry. So let's take the example again where we have our achiral molecule. You probably can't see it as it's drawn right now, but if I were to just take this molecule and I'm going to turn it in my mind's eye, I'm going to turn it so that I'm looking kind of through this carbon atom from kind of the top, if you will. So I'm looking down onto it. It would look something like this. Now, if you can't see how I'm doing this in your mind's eye, this is where model kits are very powerful. There we go. So that's just another way of looking at this molecule. So this molecule and this one are the same thing. All I've really done is change my viewing perspective from here to kind of on top, looking down. And there's going to be this hydrogen on my left and this one on my right. This bromine will be going top down. This hydrogen will be going bottom down. Or sorry, OH, hydroxide, or hydroxyl. So this is what we have here. Now, if I were to imagine there's a mirror right here, this side of the molecule reflects onto that one. So there is definitely a mirror plane through this molecule that cuts this molecule in half and mirrors one side to the other. Now, you wouldn't do this with a carbon because you can just tell there's not 4 different groups, so it's achiral. But I just wanted to show you that there's also a mirror plane through the molecule that also tells you it's achiral. So let's see an example of that, a little more complicated example of that, shall we say. Let's take this one. So now we'll put a hydrogen down here and say a bromine up there, and a hydrogen down here and a bromine right there. There is also a plane of symmetry through this molecule right here, where this side of the molecule reflects onto that one. This is also a chiral because there's a plane of symmetry through the molecule. You can take it to the bank. This molecule is a chiral. You don't believe me on your own, draw the mirror image of this molecule right here, and you'll see very quickly you can superimpose it. Now let's see a different example, similar but different. Same 5-membered ring. The right-hand side of this molecule so far is exactly the same as this one, right? Exactly the same. But there's going to be a slight difference. So now I've changed the stereochemistry here. I've changed the center. Here the bromine was going in the up direction. Now I have it going in the down direction. And look what happens. Now there is no plane of symmetry here. There is no plane of symmetry. That means this molecule is chiral because there is no plane. So this mirror doesn't exist. So this molecule is chiral, and I challenge you, draw the mirror image of this molecule, and you'll see that you have a hard time, impossible time, superimposing it onto itself, okay? Because it's chiral.